Okay, so let's see if I can close this a little bit thing here. Ladies and gentlemen, my chemistry class. As you can see, I'm not here today. I actually have a funeral to attend in. I actually have a funeral to attend in Sault Ste. Marie, so can't be here. However, your education is important, and I value that. So in this case, I am making a video for you guys. Today, you guys are learning two concepts, which both of them are part of the mole concept. Okay, so they will be on the test next week. Now let's look at your handout. So your handout today got this new toy. 1.2.2 mole concept. So we're going to be doing the empirical formula. Now we're going to dealing with combustion analysis. That's one part, and I will want you guys to do these practice questions. It is important to do these questions. As you know, part of the tricky thing from the half test is you guys need to be able to do these basically one mark per minute, a minute and a half. So you need to these calculations should be very fast. You should be very familiar with it and be able to do it very quickly. The second part that you will learn later on is the consecutive reaction. I'm going to go over a little bit more. For those of you who are in the biology, you kind of have a little bit of a head start since we, especially for the, since we have been talking more about the cellular respiration, it's kind of, you can think of it that way. Okay, so let's get going and let's get started on the combustion analysis. So combustion analysis, this part is essentially it's remember empirical formula and molecular formula determination. The setting is basically it's you have some sort of sample, you don't know what it is, you want to figure out what are the formulas. So one of the ways I previously talked to you about it is you use a mass spectrometer. There's a sample, you don't know what it is and what it's made up of. You put in the mass spec, so you can figure out, oh, it's 25% blah and 50% blah and 40% blah, some other blah. So in this case, combustion analysis is the same idea. You have, I'm going to get a piece of paper here. So essentially, you have some sort of hydrocarbon. Maybe I should use a darker color so maybe it'll show up better for you. Awesome. So in this case, you have some sort of hydrocarbon, so which is C something, CXHYOZ. Okay? We don't know what these numbers are, we're just making things up. So, plus oxygen. Now, if you remember your grade 10 science correctly, you will remember that complete combustion of hydrocarbon fuel, you always get CO2 plus H2O, right? So in this case, you kind of want to know this, you want to figure out what this part is. Okay, you want to figure out what this part is, and you can figure out the formula of these based on the CO2 and H2O. Okay, so right now, that's a basic formula, basic concept. Now let's look at your handout. Okay, and we're going to do this sample question together, or I will do it, and you look at it and follow it. Okay, so we have menthol. We don't know what it is. Blah blah blah. Composed of C, H, and O. Yay! We know the mass of this sample. It makes so many grams of CO2. It makes so many grams of H2O. What's the empirical formula? So in this case, we want to find out what the empirical formula first. Now, the couple of things is this. You want to find the mass of each compound to mole. Okay. Now, we have this little table here, and in some ways, this is a table setup that's not too dissimilar to what you have done before. But the game plan really is this. And you know that I always do the game plan thing. So the game plan, step 1, find mass of carbon and hydrogen from CO2 and H2O. Now, after you find the mass of that, you can find the mass, of oxygen from others. So after you find the mass of this and the mass of this, you know the sample has this mass, so you can subtract the mass of this two from here. After that, you convert all these three things. Convert this, you have the mass into mole. Convert mass of C, H, and O into moles. Now and the next step, what you're gonna do is of all the mass number, you're gonna find out which one is the smallest one and divide all the other mole numbers by the small one. Okay? Divide by smallest, and using that, you'll find the nearest whole ratio. This is very similar to what we have done previously when we're doing the determining empirical formula, sorry. Whole number ratio. Okay, so let's get this started. Blah, blah. I'll use this bottom part of this. So step one, find the mass of this. So let's see. So we have, so CO2, the mass of CO2 is 0. Make sure you guys can see, 2829, right? That's what it says here. And the mass of water is 0.1159 grams. Awesome. So we need to find the mass of this carbon and mass of hydrogen from this compound, right? So what we're going to do is this. Mass of carbon from the CO2. Keep in mind, the molar mass of CO2, so we have this whole, so the whole CO2 is 0.2829, right? Now, if you remember, oxygen is about 16 each, carbon is about 12.01. So in this case, if you compare this, of this whole molecule, the molar mass of this whole entire molecule, it will be 12.01, and then you have 12.01 plus 16 plus 16, that goes up to 44.01, right? That's the entire molar mass, molar mass of CO2. So of this 44.01, 12 of it is the carbon. So in this case, we can multiply the mass of the CO2 by basically 12.01 divided by 44.01, because this is that's the carbon that is of, molar mass of just carbon, molar of just carbon. This is molar mass of entire CO2. Okay, so when you multiply this in the calculator, you should get 0.077201 grams. Okay, so that will be the mass of the carbon. Now we're going to do the same trick with a hydrogen. So mass of hydrogen. Now again, the sample tells you that, the sample of water is 11.59. So it's 0.1159 grams. So again, the same idea goes. Water is 2 hydrogen plus 1 oxygen. So you have 1.01, that's 1 hydrogen. The other 1.01, that's another hydrogen. And then you have 16, that's the oxygen part. So These two add up together gives you 16.02. That's the total molar mass of water. Now we just want to know how much the mass of the hydrogen. So it's the hydrogen part of it is 2.02. Okay. So when you plug that in the calculator, this times this here should give you 0.012992. Yes, I'm carrying a lot of decimal place, but why not? Okay, the more decimal place you carry during the calculation, the closer and accurate your result would be. And in some ways, it's easier later on. Okay, so we found the mass of, well, now go back to the game plan. We found the mass of carbon, we found the mole of hydrogen. Now we found the mole of oxygen from the others. So what you do is this. You know the mass of the sample, okay, 0.1005. Out of this, you have 0.07 is carbon. You have 0.01299 is hydrogen. You can subtract this, subtract these two, will find you the mass of the oxygen itself. So let's do that. So mass of oxygen. So in this case is 0.1005 grams. That's a mass of the sample minus 0.077201. That's the mass of carbon from before. Plus mass of 0.012992. Okay, that's a mass of hydrogen. From that, you find out that the mass of oxygen would be 0.010307 grams. Okay. So now we have the mass of carbon, hydrogen, and oxygen. Now, if you remember your game plan, step 3, you convert the mass of these into number of moles. Okay. So this is relatively simple, and I'm going to do this in a table format. Carbon, hydrogen, oxygen. So in this case, the mass is here, 0.077201, 0.012992, 0.010307. So all these are grams, right? We want to convert them into moles. So in this case, the molar mass, we need to know molar mass or atomic mass. So molar mass of carbon is 12.01. Hydrogen is 1.01. This one is 16. So right now, this divided by this will give you, no, this is a part that I pre-calculate this. Let's check. So I pre-calculated this. This one is 0.006428. Okay. Now this one I didn't pre-calculate, but something divided by 1.01 is probably not that far off. So 0.012992 divided by 1.01. That gives me, yay, barely any difference. 0.0128633. Let's do it that much. And this one divided by 16, I pre-calculated, I got 0.1236441.875. Okay, so I found the number of moles of each of these carbon, hydrogen, and oxygen from the sample. So the game plan is step 4, divide by the smallest, and then using the nearest whole number ratio. So very obviously, this will be the smallest one. So all these will be divided by 0.0006441.875. 0.000644187.5. This will just end up being just 1, okay? So this divided by this, and did I do this ahead of time? I hope so. It's not as fun if I didn't. So if I divide this, no I didn't. So sucky. So anyways, 0.00646428 divided by 0.123644187.5. Hey, it's 99.97. That's 8. That's pretty much equals, yeah, let's look at the screen. So in this case, yeah, that practically would be a 10. If you divide this together, I previously done this. This is practically 20. And this is practically 1. So in this case, the empirical formula meant, okay, so the empirical formula for this compound, menthol, hey, that's in your cough drop as well as a lot of gum, would be this here. So menthol from this thing here, menthol will be C10H20O just by itself. That's empirical formula. Okay, so we solved the first part. C10H20O. Now what we need to do too, the second part is this. If menthol has a molar mass of 156 grams per mole, what is its empirical formula? No, molecular formula. So what we need to do now is actually find the molar mass of this empirical formula, because this is just the empirical formula. This is the empirical formula. We want to find the molar mass of this empirical formula and compare it with this 156. Is 156 the same number? Was it double that number? Was it triple that number? Then we can figure out what is the molecular formula. Okay, so let's figure this out. Carbon is 12.01. There's 10 of them. Hydrogen is 0.01. There's 20 of them. Oxygen is 16. So in this case, 120, 120, 20 is 20.2, and 16. So 0.3, 156, practically 156. So in this case, oh look, the molar formula of this, molecular formula of this, molar mass of this empirical formula is the same as the molar mass of this. Hence, this is also the same as the molecular formula. Okay, so you're comparing the molar mass of this empirical formula. You want to see the molar mass of the actual substance. What ratio is it? Okay, and then for us, we found that it's the same thing. So we don't have to double it and whatnot. So this happens to be also the molecular formula. So coming back here, so the molecular formula would also be C10H20. Okay, so this is the part of the video that talks about determining the empirical and molecular formula by using combustion analysis. Please make sure you do these 2 practice questions. Okay, Miss Aragona will come in later on to just check in on you guys and answer any questions. Again, here is the game plan. Okay, you might want to take a picture of this And here's my work and calculation. Okay. Move this a little bit. Here's my work and calculation. I'm going to move the camera so you can see a little bit better. Okay. And yeah, I'll make the second video for you. Bye.